I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain, life,
the universe.
Hello, welcome to The Naked Scientist. This is the show where we bring you the latest breakthroughs in science, technology and medicine, and that's with me, Chris Smith, and with Phil Sansom.
This week, we're exploring the scary science of avalanches, how they happen, how to avoid them, and we hear the true story of a man who survived being caught inside one.
Plus, in the news, measles cases triple, have physicists really discovered a new fundamental force, and as we lurch into the office Christmas party season, the scientifically proven solution to hangovers. We've tested out the recipe. Sort of.
The Naked Scientist podcast is powered by ukfast.co.uk.
First this week, cases of measles have tripled since last year, new figures from the World Health Organization reveal. In 2018, numbers were already significantly higher, with nearly 150,000 people dying of the infection and an estimated 10 million infected.
Yeah, the United States has reported its highest number of cases in 25 years, and 4 countries in Europe, including the UK, lost their measles elimination status following long-term outbreaks of the disease. This week, in the grip of a massive outbreak, the Pacific island of Samoa declared a curfew and a mass vaccination campaign to try and stop it.
So why is this happening? What will be the consequences and what can we do to stop it? Well, Freya Jeffcott studies disease outbreaks at the University of Cambridge. She's with us now. Why are we seeing these enormous escalations in numbers?
Well, I guess the short answer is that vaccination coverage has dropped. But then when we try and understand why vaccination coverage is dropping, we have to look at sort of individual countries and take it region by region.
Why is measles such a scourge?
Measles is incredibly infectious. I think people somewhat underestimate quite how infectious it is. So if, say, none of us were vaccinated and someone with measles was walking around, that one person would be expected to infect maybe 16 to 18 other people.
How would that compare with, say, flu? Because that's infectious too.
Well, so I think a really good point of comparison is maybe Ebola, because that's also in the news at the moment. Ebola is typically, you could expect a case to maybe infect 1 or 2 other people.
So yes, it is the king of infectious viruses then.
Very much so.
And so the point is that once it gets a toehold, it really goes to town quickly. It spreads like wildfire.
It's incredible. I think that Samoa makes a really good case for this. So just since October, they had 4,500 cases. And we're talking about a country with only 200,000 people. And
it's not trivial once you catch measles, is it? Because the death toll, I mentioned there in the introduction, 150,000 people that we know about in 2017, 18. Each year we're seeing these big numbers. That's probably the tip of the iceberg, though, isn't it?
Absolutely. I think this is one of the things underlying low vaccination rates, especially in North America and Europe, is that we've largely forgotten quite how dangerous it can be.
And when people talk about vaccines, how does this actually work to curtail the spread of these things, and why are we getting low uptake of vaccines?
So the measles vaccine does 2 things for us. It protects us on an individual level, so we can't get sick. But when we have a 95% of the population protected, or ideally even more, then it can't spread through populations either, which is great because not everybody can receive the measles vaccination, like babies under 1, for instance. So this protects them too.
And this is the concept of herd immunity, isn't it? The idea that you've got protection from being part of that herd where the vast majority of them cannot propagate measles.
Yeah, absolutely. And I think this day and age with sort of international travel and such, we've got to understand that the community we're trying to protect is much larger than just our local village, town or country.
So Samoa have had a sort of lockdown, they've had a curfew. Why will that work, or will it indeed work? Because at the same time, they've also started a mass vaccination campaign because their vaccine rates are only about 30%. They now say they've tripled them to about 90%. So they're close to the magic number that you're highlighting, but not quite there.
Unfortunately, Samoa was in the situation where they had a reactive measles vaccination, which is where sort of the cat's already out of the bag and you're doing everything you can to sort of limit the damage. So essentially, they told everybody to stay home to try and stop people who were potentially unvaccinated mixing with infected people. Before that, they'd actually locked down the schools and stopped children going to any public places.
What's the lesson that we can learn from this, and what might be, therefore, the next steps in trying to deal with the fact that we're just seeing this enormous escalation in numbers around the world?
Obviously, the answer is getting vaccination rates above 95% across the world. But I think for North America, Europe, the Pacific Islands, we've got to look at public health education and science communication. I think they're really the answers to getting rates back up.
Because you've helped to investigate and control Ebola outbreaks as well in your career, haven't you? And there must be some parallels here, because one of the things that emerged when we had the huge outbreak in West Africa of Ebola in the last 5 years ago, 2014, wasn't it? People said that there was so much misinformation floating around that the local population didn't know the right thing to do not to catch Ebola.
Ebola is slightly different in that it is such an unusual situation. Ebola outbreaks are really quite rare, that when they happen and these large, quite strange responses, people in sort of spacesuits running around, it's quite a terrifying and novel experience for people. So then everything you're doing is kind of weird, intimidating and unfamiliar. I think maybe we have less of an excuse on the measles vaccination front. And again, we're aware that this is an effective, readily available way of protecting ourselves against this.
So don't take risks.
Yeah.
Freya Jeffcott, thank you very much.
Now, moving to something even smaller than viruses, you might have heard some news going around recently about the discovery of a supposed fifth fundamental force in physics. This comes from the Atomiki Institute in Hungary, where a team of scientists claim to have found evidence for a new fundamental particle that they're calling X17. They first detected this as a blip on their instruments back in 2015, and now they claim to have repeated it.
If it's true, it completely disrupts the current models of physics, which don't have any room at the moment for a brand new particle. But lots of people are sceptical because no independent team has yet replicated the findings. To get an independent perspective, Phil went to visit physicist Ben Alanak.
The scientists are claiming to have discovered a new particle which hasn't been found before.
That seems like quite a big deal.
That would be a huge deal if it were true.
How do they claim to have discovered this?
Okay, so they are doing nuclear collisions, the hard, dense centres of atoms, and they're bombarding them with protons and making heavier nuclei in excited states. These nuclear excitations can lose energy by giving out particles of light. And if the energy is high enough, the particle of light will then turn into an electron-positron pair. So by analysing the angular separation, they can tell something about what's going on.
How are they actually detecting this stuff? Because you can't put on a pair of zoom-in glasses and go, oh, there goes an electron.
No, that's right. They've got fancy kits to measure the electron going through it. They're basically detectors arranged around the point of collision. Positrons and electrons go through the material and leave charge deposits. And so then you read out that with electronics and you can tell where it's gone and so on. If you've got the theory right, you should be able to tell how often they come out with a particularly wide angle. And they're finding that at rather large angles, 120 degrees, there are far too many of them coming out. And that's consistent, they say, with the production of a new particle, which is decaying into the electron and positron.
What's the name of this new particle and what's it do?
Well, they've called it X17, mysteriously. X because they don't really know what it is, and 17 because it weighs 17 million electron volts worth of energy. What does it do? We don't know.
Why are people relating it to a quote-unquote fifth force? What's that all about?
Actually, particles and forces are kind of different sides of the same coin. When you go deep into the quantum theory, you find that forces are given by the exchange of many quantum particles. Best example probably is the electromagnetic force. You're aware of magnets repelling each other if you put the North Pole to the North Pole. But really what's happening is the magnets are exchanging particles. The particle, the photon, is producing the force. So many, many exchanges, many times a second. In the same way, this X17 is a particle, but exchanging it a lot would produce a force.
What would that force do?
It would give you a force between electrons and nuclei. That's all we know. It could do other things as well, but seeing as it's only been observed in interactions with nuclei and with electrons and positrons, that's all we know about its supposed effects.
What do you think? Is this the real deal or is this a little bit overhyped?
I'm sceptical for three reasons. Firstly, why haven't other experiments seen this? This isn't a particularly heavy particle. It should have been observed in other collider experiments. The other thing that makes me feel a bit nervous is that the same authors, or at least a large subset of them, have made three other discoveries of supposed new forces in the past 20 years or so, and they're all incompatible with each other. Thirdly, there's an issue with the calibration data. So I looked at the scientific paper that they wrote today, and the calibration of the angular separations is not as good quality as you'd want. So it's not a killer or anything, but it just makes you a bit suspicious that maybe there's something a bit off in the calibration that's affecting their results.
It sounds like this is almost a boy who cried wolf type situation, potentially.
Well, you never know. I mean, at some point they could be right. That's why good science is to check these claims with a different experimental setup and, different number of people with a different methodology. And then you'll know for sure, hopefully.
Well, if it's not a new particle, then what is it exactly?
Well, it could be some problem with the experiment. I mean, these are difficult experiments to interpret sometimes, and you need to calibrate very precisely. Tiny uncertainties and errors in the wrong direction can lead you to the wrong conclusion sometimes. So it could be something like that if they're unlucky.
And if it is a new particle and you had first shot on naming it, what would you call it?
The Heaven 17.
Certainly a dramatic name. Thanks there to Ben Alanak from Cambridge University. And if you want to read the paper, it's available online as a preprint if you search for X17 particle.
What would you have called it then?
The Sanson particle.
Naturally.
Instantly.
So what we were trying to do with this paper is to demonstrate the ability to type using brain signals, anywhere between approximately 4 and approximately 8 words per minute, a factor of between 2 and 4 faster than what's been demonstrated before.
Each month, the eLife podcast talks to some of the world's best scientists. Join me, Chris Smith, as I hear about breathtaking discoveries hot off the press. Find the eLife podcast on iTunes or listen and download for free from nakedscientist.com/elife.
Still to come, chemists come up with a scientifically proven remedy for a hangover and the science of avalanches. We talk to someone who survived one.
Before that, though, the UN's annual climate change conference, COP25, has been taking place in Madrid this week. The conference's aim is to take the next crucial steps in implementing the global carbon-cutting proposals that were agreed 4 years ago in Paris.
But are we really on the road towards a carbon-neutral future? And if not, what's it going to take to get there? Chris sat down to untangle the headlines with two climate experts.
My name is Eric Wolfe. I'm a professor in the Department of Earth Sciences in Cambridge.
My name is Elliot Whittington. I lead the work for the Cambridge Institute for Sustainability Leadership around engagement between policy and business, which is a strong focus on climate change.
We heard a few years ago people saying, look, we're in trouble. If we carry on the way we're going, we will have irreversible climate change. And everyone said, this is ghastly. We must do something about this. Governments all around the world signed up and said, yep, we're right behind this. We're going to accept these targets. We're going to make a difference. I'm not seeing much action.
We haven't seen action that is coherent with the scale of the problem, but we have definitely seen action. Before the Paris Agreement, people were sort of saying we're on track for 4.5 degrees. After the Paris Agreement, if that agreement is implemented fully, we're down to about 3.5 degrees. We are bending the curve. Practical things like the number of coal-fired power stations in Europe, the US, China are far less than people predicted we're going to be. So action is taking place. What we really need to do is vastly accelerate it.
What will be the consequences? If we do carry on the present trajectory, what do models predict?
If we carry on literally the present trajectory, in other words, if people don't even meet the commitments they made in Paris, then we'll end up with a global warming of about 4 degrees. If they meet the Paris commitments, it's more like 3 degrees. And
by when?
By 2100. And if people go and meet the Paris Agreement, then 2 degrees, maybe 1.5 degrees. The difference between those numbers is a lot. So at 4 degrees, the Arctic sea ice is definitely gone. The whole of the Greenland ice sheet, which contains 6 metres of sea level roughly, is certainly vulnerable, and part of the West Antarctic ice sheet as well. So then, potentially, with that 4 degrees, we're talking about committing ourselves to sea level rises of 5 to 10 metres. Well, there are island nations that have been talking a lot this week whose average height above sea level is 2 metres.
If one considers the impact it'll have on the average person's lifestyle in order to achieve the kinds of reduction in emissions that we're striving for. Can you put that into practical terms for me, Elliot, in terms of what would I have to give up in order to do my bit?
A net zero economy could be a much more pleasant place to live than our current economy. Better designed towns, cleaner air, better diets. There are more and more people who are thinking about their diet and they're thinking about their health, they're thinking about animal welfare, other concerns. And so we are shifting. We are realising that actually our current diet is probably a bit too much sugar, a bit too much processed stuff and a bit too much meat, and it's good to reduce that. We just carry on that trend and we will be on a good track. It is not the case that we should see a net zero economy as inherently hair-shirted and punitive. How we travel and how we eat are the things that will change most, but we can still travel places, maybe not quite as quickly and quite as far all the time.
Are you optimistic, Eric?
I'm reasonably optimistic in the sense that I can now see how it can be done. I'm a little less optimistic because obviously there are some countries that just aren't engaging with the process properly at the moment.
Like?
We can't deny that the United States is saying that it's going to pull out of the UN climate agreement. That's a worry that there's a country that for at least the next few years is not going to engage with the process because we don't have a few years. We can't afford to wait 10 years and then start the process because otherwise we won't make it.
Let's hope it doesn't come to that. Thanks very much to Eric Wolf and Elliot Whittington from the University of Cambridge. And incidentally, there's a longer version of that discussion available as a special edition podcast on our website at nakedscientist.com/specials.
Now, staying in the realm of things that are hot, could the possibility of sex influence how we present ourselves to others? A paper recently published by Gerrit Birnbaum and her colleagues in the Journal of Experimental Social Psychology suggests that, surprise, surprise, yes, we do. Anglia Ruskin University psychologist Helen Keyes, who wasn't involved in the study, took Katie Haler through the findings.
They're trying to find out whether we would change our own behaviour when we feel that we're around a potential sexual partner. First of all, what they looked at was whether showing people videos of people making out would make them more agreeable or give more ground in an argument with another person. So first of all, they divided participants into groups where one half would have seen videos of people making out and the other half would have seen just control videos of a couple engaged in a conversation. And after this, heterosexual participants were paired with a stranger of the opposite sex and they were asked to role play a disagreement or an argument. People who had seen this sexual imagery or people who were sexually primed reported giving more ground in that argument. And this was true for both men and women. Then they wanted to look at what happens when we're more subliminally primed. So this is quite interesting. Participants had to fill out quite a long dating questionnaire about themselves. Then half of these participants were subliminally shown sexual images of semi-naked men and women, and half of the participants were subliminally shown images of nature. And by subliminal, I mean these images were flashed up for less than 30 milliseconds. So participants weren't aware that this was happening.
Were they watching watching a film or something whilst these images were just flashing up?
They were doing a really innocent task of choosing between like Thai food and Italian food. Little did they know that they were seeing some saucy images. Following this, each person was shown another person's dating profile, an imaginary profile that the experimenters had manipulated. Then the participant went to make their own dating profile. And what they found was those who'd been subliminally shown sexual images conformed much more. They brought their responses much more in line with the dating profile they'd just read. So if they had initially been opposed to cuddling, they now kind of moved a little bit closer to cuddling on the cuddling scale. They conformed more if they'd been sexually primed, but not if they hadn't been sexually primed. And then finally, they wanted to know about explicit untruths or lies we might tell about ourselves. So they looked at how we report how many sexual partners we've previously had. Interestingly, they asked people to either anonymously report this or report it in an online chat with a potential partner or somebody they thought was a potential partner. And they found that for both men and women, people revised downwards the number of sexual partners they reported having if they were in the online chat compared to an anonymous forum. That's not surprising. But interestingly, this was only for people who had watched sexually explicit material. So again, people who'd been sexually primed, had their sexual system activated, they reported downwards, both men and women, the number of partners they had. And this is just conforming again to what you would imagine the other person wants to hear.
What do you make of this?
I think it isn't surprising. I think it's largely harmless and quite a nice positive thing to think that we might accommodate other people, or we might engage in relationships with new people in a way that we think is going to establish that relationship or encourage that bond between people. So it's actually quite a nice finding, but it also might tell us that maybe when we begin a relationship with somebody, or we're exploring that possibility with somebody, they may be presenting themselves in a way that they believe is conforming to what we would like of them, and to just bear that in mind when we're establishing that relationship.
Or indeed, you might behave slightly differently to the way that you would truly feel about something.
Absolutely. And you would hear people saying sometimes, oh, you've really changed around this new person. And it's nice to have a study to say, well, that's not that surprising, and I'm engaging in really pro-social behaviour here.
I suppose it can't be all that bad. After all, I heard compromise is key to a good relationship. Thanks there to Helen Keyes.
And of course, they always say that sex sells. The naked scientist. It's popular for a reason.
Yeah, and it's our personalities.
Yeah, quite, absolutely. Well, now the office party season is in full swing. Here are some crucial research results that you need to know about. Chemists in Mumbai have been searching out the perfect hangover cure. They've tested all sorts of fruits and foods and vegetables in the lab to find out which ones can help to break down the nasty byproducts of booze.
And while it might not actually represent what goes on inside your body, they did come out with quite an interesting concoction. I went to get the opinion of a slightly hungover scientific onlooker, and that's theoretical chemist Alex Thom.
So they found that various fruits and vegetables actually change the way alcohol is degraded in the body.
Are we talking about treating a hangover?
Basically, yes. I mean, it's the products when you drink alcohol and it ceases to be alcohol and it turns into some nasty things and then eventually turns into fat.
Okay, explain how they investigated this.
Okay, so they didn't actually use any live subjects. They got some of the enzymes that are used in alcohol degradation called dehydrogenases, one that turns alcohol into acetaldehyde, and that works fairly slowly, and a second one that takes acetaldehyde and takes it to acetate. And it's the rate of the two fighting against each other which keeps a steady state of this acetaldehyde, which gives you the hangover. If you make acetaldehyde faster than you get rid of it, you get a build-up. And so they did separate tests on these two enzymes with all manner of different fruit juices and vegetable juices.
What fruit juices and vegetable juices?
So they went down to the local market in Mumbai and picked up basically everything they could find, from pineapple, papaya, carrots, coffee, spices, coconut milk and coconut water.
Sounds like a horrible hangover concoction if you mix it all together.
They did them separately, but then they tried to work out what would be the best combination, and they had a panel who decided whether or not this concoction they were going to make was pleasant. The panel universally said that anything involving vegetables wasn't a very nice drink.
That makes a lot of sense to me. How good is this science? Is this actually testing whether these things are a good hangover cure?
Probably not, because they're doing this in vitro in glassware rather than in the liver. All manner of other things are probably going on in the body. So take this with a pinch of salt as to actually whether it does the same thing in the body as in the test tube.
What was the weirdest thing that they tried, in your opinion?
So they tried cheese as a hangover cure.
Cheese?
Cheese, yes. And it actually appears to be a hangover cure. What was an interesting one I found was that coffee, which they tried, actually has the opposite effect on hangovers, that it causes your hangover to get longer.
That's mind-blowing. I always drink coffee when I'm feeling any sort of headache.
Same here. So I've deliberately avoided a coffee this morning.
Have you got a hangover this morning for the sake of science, can I ask?
I'll say I had a relatively late night at a friend's birthday, so I wouldn't say I'm entirely fresh this morning.
Right. Well, this is the ultimate test because you're in the perfect state. Now, did the scientists find what they think is the perfect hangover cure?
They found their best combination that would get rid of the acetaldehyde quickly, and it was a combination of pear, sweet lime, and coconut water. So we've got 3 different liquids here. So there's some pear juice, freshly squeezed, some lime juice, freshly squeezed, and a little bottle of coconut water, and we're going to mix them together. I have a little cocktail shaker here, just for science, and So it involved a bit more pear juice, a third of the same quantity of lime juice. It's probably about that much.
It doesn't look too appetizing yet.
Yes, it's got a slightly murky brown colour, and the same amount of coconut water.
Well, it's still murky brown. All right, bottoms up.
Bottoms
Cheers.
up. Ooh. Actually, it's quite nice. The lime really gives it a zing, and it's certainly waking me up at the moment. Actually, I could just drink this for breakfast, actually.
And the actual ratio for the hangover cure is 65% pear juice, 25% sweet lime juice, and 10% coconut water. Try whipping that up with a headache, right? Thank you to the University of Cambridge's Alex Thom, who was discussing a study from the journal Current Research in Food Science.
And if you want to follow up on any of the things we've been discussing this week, there'll be transcripts and the references to the studies behind those reports on our website. That's nakedscientists.com. Now it's time to head over to the mailbox. This is the part of the show where we read out some of your correspondence. And Adrian's been on our Facebook page, and there he's written, why would a used battery, AA or AAA, bounce on its end more than a full one? Phil, any insights?
I actually thought this was a really interesting question. In fact, I didn't expect it to be true. Sometimes people say that you can tell a flat battery from a good one because the flat ones bounce, but I actually thought it was just a rumor. It turns out, though, that scientists from Princeton did a study testing this by dropping batteries down tubes, and the flatter ones do indeed bounce higher, at least up to the point where they're half drained. To find out why, they dissected the batteries and saw that at the negative end, which starts out containing a zinc gel, it slowly turns into a ceramic as the battery drains and the zinc oxidizes. That ceramic gives it the extra bounciness. So the dead batteries bounce story is half true. The key thing is they might still have half their charge left.
I think I'll stick with the multimeter, though, if that's all right. Probably a bit more reliable, isn't it? And quieter.
Think so.
Thank you very much, Phil. Well, when you're not dropping your batteries, why not drop us a line to chris@thenakedscientist.com or tweet @nakedscientist if you've got something you want mentioned here on the mailbox.
Music in the programme is sponsored by Epidemic Sound, perfect music for your audio and video productions.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
This week, we're exploring the terrifying force of nature that is the avalanche. We'll be finding out why these happen, how do you avoid them, and if you're unlucky enough to encounter one, how might you be able to survive it?
Avalanches are most common in the northern hemisphere between now and March. So if you live in a mountainous area, or if you're going to one soon on holiday, it's important to stay vigilant. And someone who knows that better than most is Lawrence Jones, who 20 years ago was caught in an avalanche and lived to tell the tale.
I was with a group of friends and we were in a resort called Alpe d'Huez, which is in the French Alps. It's got a mountain called Pic Blanc. It's known for having the longest black run in the world, and it's a fierce mountain. It's a fierce black run. I opened the shutters the next morning and it was cloud, and I came downstairs pretending to have all that bravado. Oh, I'm really looking forward to today, chaps, you know. But I actually was terrified. But they said, oh, don't worry, we'll head up to the mountain rescue hut and see what they have to say about it. And even though the lifts were closed, they managed to talk the lifties into opening both lifts. Off we went. Off we were going up to the top, and sure enough, all the signs for every single run closed, everything saying fail may, fail may. And we traversed across the very top of this ridge, where there were lots of signs that essentially in French were reading, only idiots go past this point. And it was amazing. There was no two ways about it. And when we stopped, I said, this is the most amazing experience I've ever had. I said, I will never ski on piste ever again. This is so good. We went one at a time. I think I was the second to last. So I was the penultimate person. And there was a moment where Danny overtook me. And as he went past me, he dug me in the ribs, messing around. And I fell off my snowboard. I was going very slowly at this point anyway. And so I unclipped the bindings and I stood up and I waved, and I saw all the boys over in the distance waving and waving and waving. What now I understand was they were frantically waving, and I just thought they were being enthusiastic. And so I enthusiastically waved back. And I didn't hear anything. To this day, I don't remember anything. The next thing I realised was I was suddenly enveloped in this force of nature where I was being pushed and pulled and dragged, and I tumbled down the mountain, being sucked under the snow, and suddenly I'm above it and then I'm under it. the whole mountain just picked me up, and the whole mountain went down together.
Absolutely terrifying, isn't it? We'll find out what happened next to Lawrence later in the programme. And we've also got a neat kitchen science experiment coming up to show you how avalanches work. If you'd like to take part, you'll need a baking tray, some salt, some corn flour, and some regular flour.
Yeah, plain or self-raising, I think
Either
will
will do.
when they fill. Now, in the meantime, we've got with us Mark Diggins. Now, he's the coordinator of the Scottish Avalanche Information Service, and also with us is Jim McElwain, who is Professor of Geohazards at Durham University, and they're going to help us to unpack what happened to Lawrence. Now, Mark, you're in charge of producing the avalanche hazard forecast for Scotland. Why might there have been a high avalanche risk on the day that Lawrence went skiing?
There are 5 typical problems. Wind. The wind destroys grains and makes a sort of compact, small grain layer. There is something called a persistent weak layer, where you have a layer of grains or crystals underneath the surface, and you actually have no idea that they may exist. But what's happening is they may be developing and getting weaker and weaker. And then the next is new snow, of course. So if you get lots of new snow, logically, that's going to load a slope and slide away. And then wet snow, which is obvious, warming or rain, which will make the snow turn into a sort of slurry. And then gliding snow, which is a sort of spring effect where you get big cracks and slowly the snow is creeping down the mountainside. And then finally, what we have and other countries have is a problem which is a cornice, which overhangs a sort of a slope. And if it collapses, that can produce a big trigger. But the 2 key ones are the wind slab and the persistent weak layer underneath the surface, which it sounds from Lawrence's case that this may well have been one of the culprits.
Jim, does that jibe with your sort of research into avalanches? Do you look at the same sort of factors?
Yeah, exactly. I mean, it's precisely how Mark described it. I'm at the sort of more theoretical end of it, but it's all these factors. If the load from gravity in the snowpack exceeds the weakest layer, then the avalanche will occur.
And Mark, the factors that you described, those are things that you can tell without having to actually potentially go onto the slope. You could potentially observe those from a distance. Can you actually, if you go and look at a patch of snow, tell, hey, that's a big avalanche risk?
One can, if one is aware of what you need to do when you're going into the mountains. And that's the real challenge for recreationists, people going skiing or climbing, is the boundary between having a fantastic time in sunshine and having some terrible event occur is unseen. And so what you really need to know is what's gone on. So you need to know the history of the snowpack. You can't just turn up and expect to know the complete picture. You need to have some understanding of what's gone on before in the days before.
Well, let's find out actually what happened next to Lawrence.
2 Swedish guys who'd followed us up, taken a higher traverse than us, and as they stopped, those 2 triggered the thing off. They just saw this thing obviously crack at the top and then just gather momentum, gather, and then just hit me like a thunderbolt. As a younger man, I played a lot of rugby, and there are moments, not very often, but there's a moment every now and again where you get caught up in a scrum or a ruck of some sort, where you are literally lifted off the ground and there's nothing you can do about it. And you may as well just stop fighting. And you realise I'll save my energy till I'm unpeeled and I can get back out again. It was like that, but 1,000 times more. I was sucked underneath all the snow and then the lights were out. And the thing I remember most about that is the eeriness, this terrifying silence.
Jim, when Lawrence just said there that the avalanche got triggered, what exactly does that mean?
Like Mark was saying, it's most likely it was a slab avalanche. So you've got hard, rigid snow and it's on top of a weak layer. And if you put extra loading on it, it can cause the weak layer to fail. And then the fracture can propagate extremely quickly. So this is what the trigger was most likely. These Swedish people, they overstressed the weak layer and started it.
And Mark, would you concur with that? It's basically you're putting more mass on the slope above where the group of skiers involving Lawrence were.
It may not be as clear as that. So it could be that when Lawrence went off his snowboard and was on his feet, he may have penetrated the snow. So if you imagine when you're traveling along a snow slope, you have a globe of effect underneath your feet. And if that globe coincides with a weak layer, you get a collapse underneath that weak layer. That then can propagate, and it can propagate great distances, and that's relative to the density of the surface layers. So if it's harder, it'll propagate great distances. If it's not so hard, it won't travel as far. But it could well be that Lawrence, by coming off a snowboard, he could have initially weakened the slope, and then the final straw, if you like, was another pair of skiers on that slope could have made it release again.
Just quickly, producer Amalia Thomas has an experiment that she'd like to demonstrate. So if at home you've got your baking tray, corn flour and normal flour and salt, it's time to follow along.
So I put my baking tray flat on the table, and on it I spread as evenly as I can coarse salt. On top of the salt, I put the cornmeal, again another thin layer of cornmeal. So now I put the plain flour on top of the yellow cornmeal. And I'm going to slowly tilt it until all my ingredients avalanche. So this experiment is interesting for a couple of reasons. First of all, because the combination of salt and flour avalanches at the same angle, between 35 and 38 degrees, as snow does in real mountains. And secondly, the way that the avalanche of salt and flour happened resembles the way snow avalanches break off the side of a mountain as well.
Thank you very much to Amalia. And hopefully, if you've done our experiment for yourself, you'll be seeing the same thing. And in fact, if you have, we would love to see a photo of it. So send in images of your experiment, your homemade avalanche in your kitchen, to chris@thenakedscientist.com or put it on Twitter @nakedscientists. Copy us in, and we'd be happy to retweet that. Jim, how representative of real life, though, is that experiment?
Well, what you've got here is two sets of particles with different properties. So the salt particles are large and they're behaving like what we would call a dry granular medium. So that's like dry grains of sand. The only force between them is friction. There's no cohesion. So they're quite weakly bonded and they can easily move. Whereas the flour is much smaller. So you get electrostatic effects and effects on the humidity that makes the particles stick together. So they have a lot more strength. So you have this mixture of the different flours. I think the corn flour makes it even stronger. So you've got a lot of strength in this slab-like layer on top of this weak layer. And then as you increase the slope angle, this simulates increasing the load. So this could be like a skier moving over the top or fresh snow falling on top. And then the weak layer fails when the force of gravity down the slope overcomes the friction in between the salt particles.
Can the same science be used to explain any other natural phenomena? Or is this purely something related to avalanches?
Well, that failure mechanism is purely related to avalanches, but they're very much like all sorts of other natural disastrous geophysical flows, like pyroclastic flows, debris flows, rock slides. And we use the same mathematical models, really, for all of these different types of events.
So do you have effectively a computer simulation that you can plug in all of the parameters of, say, snowfall or an environment and work out what the likely risks are and what the likely outcomes would be if things went wrong?
Well, that's the aim of the work that I do, but we're not there yet. And I would say at the moment our models are not that predictive. So we can fix parameters to agree with past events, but we can't really say what's going to happen in the future.
Easy question to ask, impossible to answer. Well, why is it going wrong?
Well, part of the problem is until recently there's been very little really good data about how these things flow and what's going on, because normally you have a big powder cloud on top, so you couldn't really see what was going on. But now we have all sorts of great data, a lot of it from Switzerland, where we artificially trigger avalanches. So this can really give us insight as to what is happening and help us develop better models.
Can you actually put things into the snow so that when an avalanche does happen, they're carried along and you can monitor what happens?
That's a great idea, and the avalanche people in Austria are working very hard on that. The big problem is then how to collect these things afterwards and get the data back out of them, because the radio waves and things don't travel very well through solid snow. So you can't really get the data out easily while the avalanche is happening, and it's how to find these things afterwards is the tricky problem at the moment.
Jim, thanks very much. And now let's go briefly back to Lawrence, who had just been dragged away by the avalanche and was buried in snow.
I think I was something like 8 or 10 feet down, about 12 minutes or something like that. So quite a long time. I was upside down as well, so when they found me, I was in the position of John Travolta Staying Alive, you know, that dance move he does with his arm, one arm in the air. almost like Superman pointing downwards, which again wasn't very helpful when they're trying to dig me out and the first thing to do is find my boots. When you're in there, you have no idea which way is up or down. So even if you had the ability to try and dig yourself out, you wouldn't know which way to go.
Sounds absolutely terrifying. So, Mark, when this happens, how do you go hunting for people?
Well, firstly, I think Lawrence is very lucky to survive because statistics show that after 10 minutes, you've got a 10% chance of survival. So he is very lucky to survive that depth and for that length of time. It's absolutely critical then that the people on the surface have equipment that enables them to find somebody that's buried. So everybody carries these transceivers and they both transmit and receive a signal. So when you're skiing around, they are transmitting, but then if someone gets buried, those people on the surface will have to turn their machines to receive so they can find somebody. So they will take you to a sort of an area, probably about a metre square or so on the surface. But of course, if someone is buried deeply, then on the surface, the signal might be the same in a larger area. So then what you really need is an avalanche probe. And these are 3 meters, so you push those into the snow, and they're actually quite sensitive, so you can sort of tell when you've got something that's yielding. And then as soon as you find somebody, you leave the probe in, and then you have to dig down. And the digging down is also extremely tiring because you're talking about a weight of 600 kilos per cubic meter. You know, it's an enormous amount of weight that you have to move very quickly.
Jim, I want to ask you, I've also heard you can get these backpacks with airbags in for if you're free skiing, for example, that you can activate in the event of an avalanche. Why would that help at all?
They have several effects, one of which is just to shield you from impacts, which can often do an awful lot of damage. But their main effect is through something called segregation. So they help you end up on the top of the snow. So that means you're less likely to be damaged, you're more likely to be able to breathe, and you're more likely to be seen. Now, why is it that they help you stay on the top of the snow? Well, it's the same reason that if you have a box of cereal and you shake it around, then the larger lumps of cereal end up on the top. And this is through an effect called kinetic sieving. So if you have a large particle with lots of small particles moving around it, they can fall through the gaps in between and they effectively force the large particle up to the top. And in an avalanche, if you put an airbag on, you are acting like a very large particle in amongst these smaller snow grains or blocks of snow. So you've got a very much higher chance of ending up on the top of the snow.
Does that difference then between your normal size as a human shape versus with a big swollen airbag, is that enough increased size to actually bring you way up in the avalanche?
Yeah, a friend of mine actually did that for their PhD. They put a load of dummies on a slope, half with airbags and half without, and then they blasted the slope. And all of the dummies with the airbags had some part of them on the surface that was visible, whereas I think half of the dummies that didn't have airbags ended up buried deep down in the snow.
Sounds like a good opportunity to ask you, Mark, do you actually detonate avalanches? Because I know in some ski resorts they do that in order to reduce the risk.
Yes, so in many avalanche services, they control the avalanche situation by, if they leave the snow to build up, then you get huge avalanches that may come down and be really destructive. So they have a process whereby they control them. So they will fire charges into start zones. So they release avalanches bit by bit. So you don't get a whole mass coming down, but you get smaller avalanches coming down.
And Jim, why would a charge like a shockwave from sound trigger an avalanche?
It's surprisingly difficult to actually trigger avalanches with explosives. Normally you want the explosion actually to go off in the air to fire a shockwave into the surface, and it really can trigger them for the same reason that skiers do. It's just additional loading over an area. But it can take quite a lot of explosives.
Because I think I've heard it, and also I've seen on James Bond, so it must be true, when the baddie fires a gun, and unfortunately that shock is enough to dislodge an avalanche. Is that possible, or is that artistic license because it's James Bond?
That's artistic license. The energy in sound waves is so low that they're never going to trigger an avalanche.
Jim, I'm disappointed.
It's a disappointing answer, but the science is the science.
And just returning to you, Mark, when a person's actually buried, because Lawrence alluded to the fact you don't know what direction's up or what direction's down, but also you've got this enormous amount of weight bearing down on you. You must effectively just be locked in position. You're completely at the mercy of the snow and anyone who comes to dig you out, presumably.
Yes, you are totally locked in. You cannot move a millimeter. So if you're twisted or in a really awkward position, you're held in that super awkward position. And also, as you're breathing, then you slowly encase the snow in front of your face with ice. And so that starts to inhibit your ability to breathe. So it's a bit of a grim prospect.
Mark, thank you very much.
When we last left Lawrence, he had been trapped for 12 minutes, upside down and buried deep in a snowdrift. And luckily, his companions had brought along some of the crucial kit.
The transducers played an important part in everything and obviously locating me. Mine obviously was left on, and the guide, Stefan, he kept his on, and I think he flipped it to another mode, which is to search for the one that is lost. And everybody else has to switch theirs off. And then what they do is they get a very, very long pole, almost like a tent pole, one of these modern tent poles that's quite bendy, and they'll go around prodding, looking for me. Well, two things that I brought on that trip that I would never go anywhere off-piste ever again. One was a heart surgeon, and the other one was a casualty doctor. They were digging with snowboards in their hands, and the two doctors were giving out the instructions exactly what was going to happen, what everyone was to do when they were to find me. Because obviously I was completely unconscious and needed to be resuscitated. The helicopter came and picked us up, and when it did arrive, and they came out with the stretcher, and I had the worst headache you could ever imagine. And Danny was explaining to me it's because my brain will have expanded with a lack of oxygen and would have been touching the outskirts of my skull.
Chris, based on your medical knowledge, is that true?
Yeah, the brain has the highest metabolic rate of pretty much any tissue in your body. And as soon as you start to deprive it of oxygen, either because you're not breathing in enough oxygen or because your circulatory system stops, then the brain cells become more excited than they should do. And as a result, they swell. And they swell because they take on water out of the bloodstream for various reasons. And that swelling, because the skull is a closed space, if your finger swells into the air of the room. If your brain swells, there's nowhere for it to go because it's enclosed within your skull. And so you do end up with a higher intracranial pressure, at least for a short while. And that's probably why Lawrence had a bad headache, apart from the fact he'd also been probably hit by 600 tons of snow, which probably didn't help.
Yeah, that might do it. Is that something that the paramedics need to treat, or is that just a side effect of...
Well, I mean, we alluded to with Mark just now the fact that when you are deprived of oxygen, then this is a serious threat to your health because people will have brain damage because of the lack of oxygen reaching the brain if this goes on for a significant period of time. But lowering the temperature can help, as we mentioned. And equally, if people are resuscitated promptly and you can restore a circulation, then actually, usually the outcome can be pretty good, but it does rely on you being found quickly and resuscitated effectively and quickly. And obviously there's a chance that that's not going to happen. And so that's why, as Mark and Jim were saying, the outcome often is dismal for people because they get buried and it takes a long while to find them.
It is an incredible story from Lawrence. It sounds like he's very lucky. Mark, have you ever dealt with a case like this?
Yes, unfortunately, it was not a good outcome because the victims were buried to quite a significant depth and it was a longer period of time of extraction. But in terms of hearing of people that have been resuscitated after being buried for 10 minutes or so, then they were revived. It concurs with what was just said now, is that they actually had a really significant rash on their forehead, which was a sign that obviously their brain had been swelling through lack of oxygen. It's very hard to always talk about the grim aspects of going into the mountains, and hopefully we try and talk about the positive things as well.
And Jim, any thoughts further on what we heard from Lawrence?
Well, it sounds like he was skiing in a group of all guys. So the safest way to avoid avalanches is to ski with a lot of women because they have almost no accidents.
You're joking.
So there's a lot of... No, absolutely. Well, the most dangerous group is a group of all guys with one or two women. There's a lot of emphasis now on safety and group safety rather than on the physics. And it's a question of communication and how decisions are made. And it's like Lawrence says, he was feeling scared but felt he should go anyway because of his friends. And they were probably all feeling the same. And the guys were not wanting to discuss their concerns and their worries about the avalanche safety by the sounds of it. And that's a classic pattern of why these things occur.
Jim McElwain from the University of Durham, thank you very much. And also thanks to Mark Dickens, who's a pro mountain guide up in Scotland. Now, we've almost reached the end of Lawrence's story, and I'm sure you've realised it does have a happy ending. He's still with us and has become a very successful businessman. But that's not always the case, because avalanches kill plenty of people. In fact, around about 100 people every year die in just the Alps. So we mustn't forget that these are giant forces of nature, and they do have humongous destructive power.
But with that destruction seems to come new creation, because research from Swiss scientists shows that whole ecosystems may in fact rely on avalanches. Christian Rixson told Amalia Thomas how he compared biodiversity outside versus inside an avalanche zone.
In our plant study, we found in the darker forest next to the avalanche tracks about 10 different plant species. And in the central zone with the highest disturbance of the avalanche tracks, with the frequency of an avalanche every year, we had around 30 plant species.
That's 3 times the number of plant species in a place where avalanches occur regularly. But how can there be a higher biodiversity where an avalanche has been? You would think that they wipe out the ground as well as plants and animals in their path.
The effect is not that disastrous that all the soil would be cleared. It's simply that the continued disturbance by avalanches keeps out the competitive taller plants like trees and also taller shrubs. So from a tree perspective, an avalanche is clearly a disaster. However, for the smaller, less competitive plants, there's more space, more room, more light to grow, and that results in more species, higher biodiversity in avalanche tracks.
So where the avalanches happen around once a year, only the taller plants are uprooted, without really disturbing the soil, allowing a wider variety of shorter plants to flourish instead.
So the plants that grow on avalanche tracks are very different ones. You also have some high alpine specialists, which would normally only grow at high elevation. Because with the snow you can also have seeds and parts of plants going downhill and then possibly growing and germinating at low elevation. Again, simply because there's space.
And a wide variety of plants means a more healthy and varied diets for animals that live in these ecosystems. Several species of animals, including bears and deer, think that those delicious plant salads in the tracks are worth the risk of getting caught in an avalanche.
Where you have a lot of plants growing, that is also interesting for food for animals. So for example, in the Rocky Mountains, mountain caribou feed in avalanche tracks, and that not only in summer but also in winter. So when the snow goes downhill, you have cleared patches of grass, and the animals need to find food. So they go to these grassy patches where they can eat. So that's a good thing for them in winter. However, that also comes at a certain risk. So while feeding in the avalanche, there could be a new avalanche starting and taking the caribou down. And 10 to 15% of mountain caribou feeding in these avalanche tracks might in the end become victim of avalanches themselves.
But what is bad news for the herbivores like the caribou may be good news for other animals.
For example, the elusive and rare wolverine, a predator or a scavenger, actually spends a lot of time in avalanche tracks searching for carcasses. And probably much of the food in winter for the wolverine comes from dead animals and avalanche tracks. So that is obviously a disaster for the individual caribou, but for the ecosystem, it is a very important process and an important natural disturbance.
Absolutely fascinating. I'll never look at avalanches the same way again. That was Christian Rixson. He's from the Institute for Snow and Avalanche Research in Davos. You can find more about Christian's research in the Journal of Vegetation Science if you want to give it a read.
Finally, let's return to Lawrence Jones. 20 years after he survived an avalanche, he still goes skiing with his family every year. Here he is one more time reflecting on what the experience has taught him.
It does scare me with the ease that people go off-piste and the casual way it's approached. We as human beings, we like to plan things, don't we? And we'll say, well, we'll do this on this day and this day on that day. That's probably not the best way of doing it. And when not to go is a really, really important thing to consider. people should stop and think and take a responsible look at their own ability and don't feel that you need to do anything under peer pressure.
So quite the cautionary tale. Very well said. Thanks very much to Lawrence Jones. And in fact, there is a much longer, full account of Lawrence's experience available as a special podcast, which we published on our website. You can find that right now. Go to nakedscientist.com/specials and you'll be gripped.
And we've just got time for Question of the Week. And Katie Haler finds out for Elizabeth why, when it comes to colour, it's a question of hair today, gone tomorrow.
The other day, my husband found a long grey hair on my head, the first one that I know of. That made us wonder, do hairs grow out grey, or do hairs that had colour eventually turn grey?
Interesting question. Over on the forum, user Halk said that their grandmother's hair turned white in a week when her eldest son was killed in the Second World War. And user Evan AU says that both genetic factors like age and environmental factors like stress affect the colour and darkness of the colour and determine when the colour turns off and how quickly it turns off in a given hair follicle. To get to the root of the question, we went in search of a hair expert, and we found one. Desmond Tobin is director of the Charles Institute of Dermatology at University College Dublin.
Hair greying is associated with the ageing process and is characterised by growth of hair lacking coloration within the hair follicle, a little ring of stem cells embedded in your skin that makes the hair. Under normal circumstances, the colour-making cells of the hair follicle actively produce and transfer their natural hair dye, called melanin, to keratin-producing cells that make up the bulk of the hair strand during part of the hair's growth life cycle. The result, a fully coloured hair, be it blonde, brown, black or red.
But as some of us may well have experienced, hair doesn't stay colourful forever. So why?
After between 5 and 8 rounds of the hair follicle growth cycle, each of which can last up to 5 years on the scalp, parts of the hair follicle's coloration machinery slows down, which results in either not as much coloration, so grey hair, or no coloration, so white hair. And it's not just age. There's now good scientific evidence that psychosocial stress can also affect many aspects of hair growth, including hair greying. So Elizabeth, as you look at hair, you'll see it either as growing progressively white during the individual hair's growth phase, or as a new hair growing in a different colour to the others on the head from the same follicle. Thus, you might see, for instance, a black hair tip becoming greyish in the middle, even to white at the level of the scalp. Having said that, it's much easier to spot the fully white hairs against a dark background. And we do not know the ratio of fully white versus gradual greying hairs on a typical average scalp.
Thank you, Des, for that colourful answer. Next week, we'll be turning up the heat on this question from Tim.
The experts at the Energy Saving Trust and British Gas say it's cheaper to heat your home only when you need it. But my heating control panel says that it uses less energy to keep a background temperature when the room is unoccupied than it does to allow the dwelling to chill too much. Which advice is correct?
Do you know the answer? Get in touch with us. nakedscientist.com/question gives you the web form. Email chris@nakedscientist.com. You can use Facebook or Twitter. We're at Naked Scientist on Twitter. Or join in the debate on our forum. That's nakedscientist.com/forum.
And just before we go, don't forget we are running our fundraiser. It's a year since we started the fundraiser, so we're into our New Year's fundraiser now for Christmas. We do have a target. We'd love to get as close as we can to it in time for Christmas. So if you can help us out, do please go to nakedscientist.com/donate. And if you could sign up to be a monthly supporter, we would really, really appreciate that. And to give you a little bit of incentive, just in time for Christmas, if you're a donor in November or December, we're very happy that we've teamed up with underluckystars.com, who will print you a bespoke star map of where the stars were in the night sky on a date of your choosing. Could be a special occasion, the first time you tuned into The Naked Scientist, for example, or the day you got married, or the day of your birthday, or a loved one's birthday. They will print you and frame you a lovely star chart. We can do that for 3 people. All you have to do is be in with a chance to get one of these fabulous star charts. Just be a donor in either November or December, and we'll include our monthly donors in there automatically, so you don't have to do anything. We'll take care of that for you. That's it for this week. Thanks very much to Amalia Thomas, who put the programme together, and do join us next time when we're going to be rocketing up into space to figure out how close we are to a future among the stars. Are we gearing up for a second space race? The Naked Scientist comes to you from Cambridge University, and it's supported by the EPSRC and Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.